So folks, what I want to make sure we take from this, after you looked at those Grant Sanderson examples, is that we can treat functions. Here we took f of x, we took g of x, and we can treat them as if they are vectors. And the example hopefully illustrated how you could sum together those two vectors, and you could multiply one of the vectors by a scalar multiple. And once you've got that, then you just need to go through and confirm that all of the properties of a vector space hold. So once you've got a notion of what it means to add together two functions, and once you know what it means to scalar multiply a function by a number from the real numbers, then you can go ahead and start talking about this as a vector space. So in this case, here, V is the set of all real valued functions. And in this case, our underlying field will be the real numbers. And in fact, I say this later on, but our field is almost always the real numbers in this class. And then by the individual functions, what we mean are functions like f, g, and h. Those will be the vectors that live in our vector space. And by the elements of the field, I mean numbers like 3 or -2. Those will be the numbers that live in that underlying field. And we've talked about what we meant by the vector addition and the scalar multiplication for functions. So now that we've got kind of all the actors in place, let's just run through and verify the properties. Usually verifying these properties isn't a lot of work, and it feels a little redundant because you guys have worked with vector addition already, and you've worked with function addition already, and you've multiplied functions by scalars already. So when I say we've got to check these properties, as students sitting in the back of your head, you're saying, wait a minute, I've been doing this for years, of course this works. But you've never thought about it as a checklist of vector properties that you need to confirm before you can start treating the space of all real valued functions as if it was a vector space. So the first thing is notice that we just showed in that example above that if we took the function f plus the function g, we got a new function in the vector space. It was just the function f plus g. That's what you should have graphed when you sum these two together. I don't remember exactly what that graph looks like. Maybe it looks something, I don't know, like this. I'll let you guys, however it came out to be for you as you did that. And likewise, you learned what it meant to take, I think we'd look at 2f of x, what it meant to take this function and double it, double the output. That's what when we say scalar multiply a function, we mean double the output, double the range value of that function. So these two properties are both closed, meaning that when I add together two real valued functions, I don't suddenly get something that's not a real valued function. So for example, if I take the function f of x equal to the square root of x and the function g of x equal to minus x, when I combine these two together, I don't get something that now is going to output complex numbers. Or I don't get a function of two variables, x and y, or something like that. I continue to have this result when I do summation of functions. I continue to have a function of real variables. Same thing, if I take the function sine of x and I multiply it by the number -12, I don't suddenly get something that's no longer a real valued function. That's what we mean when we say that these operations are closed. Then all of the rest of these are sort of, I think they should feel, you should feel like we're kind of spinning circles here as we do this. But when I say f plus g, that I'm taking the function f plus g of x, that this is the same as g plus f of x. The reason why that is because we define function addition by simply adding the two outputs for the same input. And outputs themselves are real numbers, and so I can interchange the order of real numbers. But it is something we have to confirm, that adding f plus g, when I take the function 2 and add to it the function sine of x, I get the same thing as if I add the function sine of x to the function 2. Okay? We have to have a zero vector in this? Well, in this case, our zero vector f of x, let's go ahead and, well, we'll call it f of x, fine, is the function that is identically equal to 0. That is, if we were to look at the graph of the additive identity vector, there it is. It's the function f of x that is identically equal to 0. Why is that? Because if I take and I add that function to maybe here's the function g of x equals x, if I were to take g of x equals x, if I were to add together f of x plus g of x, what do I get? I again get the function x. And so the sum of these two functions would be right on top of it here. There is g of x plus f of x. In this case, f of x is behaving the same way the number 0 works in the real numbers, in that when I add it to this second function, I end up with the same thing. Okay. For every function, there's an opposite? Sure. If I take the function f of x is equal to the sine of x, what is its additive identity? The answer is, its additive identity is the function minus sine of x. Why is that? Because if I take the graph of the sine of x, the graph of the sine of x looks something like this, and if I were to add to it the graph of minus sine of x, what do I end up with? I end up with that zero function that we talked about, that additive identity function. Okay? So I know that this feels like you might be saying, well, no, duh, if I add sine of x to minus sine of x, I get 0. But we're trying to shift our perspective in thinking about what we're doing. I want you to think of taking a vector, sine of x, adding it to its additive inverse, minus sine of x, and ending up with the additive identity vector, which is the function that's identically equal to 0. Whatever your input is, it outputs 0. Okay? These other properties you can go through and just confirm that it doesn't matter the order in which I add these functions, or if I scalar multiply a function by the number 1, I just have the same function. And you can confirm all of these properties. So if I were to take, let's take a new solution here that's a combination of those two. So let's say y3 is equal to 2y1 plus 3y2. And let's verify that y3, which is this linear combination of these two solutions, is again a solution. So if I were to take y3 prime, well, let's see here. I would say this is the same thing as 2e to the minus 4t plus 3e to the 3t. And if I were to take y3 prime, I would get minus 8 e to the minus 4t plus 9e to the 3t. And if I were to take y3 double prime, I'd end up with a positive 32 e to the minus 4t plus 27 e to the 3t. And then if I were to plug all three of these solutions into the original ODE, I want to convince you that we have, again, a solution. That is, we get a true statement here. So if we were to do that, we'd have for y double prime, we'd put 32e to the minus 4t plus 27e to the 3t. And we'll add to that y prime, which is minus 8e to the minus 4t plus 9e to the 3t. And we will add to that, subtract from that, 12 times y3, which is 2e to the minus 4t plus 3e to the 3t. And if we do some rearranging, what I'd like to do here is I'd like to go ahead and grab together this term. This term will distribute the 12 and grab that term. And so if I do that, I've got 32e to the minus 4t minus 8e to the minus 4t minus 24e to the minus 4t. And then what we'll do is let's grab together this term, distributing the minus 12, this term. That will give me 27e to the 3t plus 9e to the 3t minus 36e to the 3t. And then what we'll do is from this, let's go ahead and factor out a 2. So if I do that, I get 2 times 16e to the minus 4t minus 4e to the minus 4t minus 12e to the minus 4t. And from here, we'll go ahead and factor out a 3. And if I do that, I'm left with 9e to the 3t plus 3e to the 3t minus 12e to the 3t. But let's look at what we've got here, folks. Let me not go too far so we can still see it. This term, this e to the 4t is my y prime, right? So there's that, is my y, and I've got a minus 12 multiplied in front of it. So that's my y 1. Let's do that again. So let's look at what we've got. This term is simply y1 double prime, right? If I took the second derivative of my y1, so we said y1 was this function here. If I took the second derivative of it, I'd have 16e to the minus 4t. So this term right here is just my y1 double prime. So I've got 2 times y1 double prime, and then I've got this term right here, minus 4e to the minus 4t, but that's just y1 prime. So that's plus y1 prime, and then I'm left with just minus 12y1. So take a second, folks, because it is critical that you see what I just did there. Okay. So let's try that one more time. My y1 is e to the minus 4t. For this term right here, I saw a minus 12 e to the minus 4t, so I wrote it as minus 12 y1. This term right here, one way to think about it is it's my y1 prime. That is, if I were to take y1's derivative, there's y1, e to the minus 4t, and if I were to take its derivative, I'd have minus 4e to the minus 4t. So that's what I'm calling my y1 prime here. And if I were to take the second derivative of y1, I'd have a positive 16e to the minus 4t. Taking a look, that's exactly what I've got there, so I call it y1 double prime, and from all that I have this 2 factored out in front. If I do the same thing with this, I'll have plus 3y2 double prime plus y2 prime minus 12y. And just to double check that, make sure that makes sense, there is my e to the 3t. That's my y2. Oops, and I dropped the 2 on there. That's my y2, e to the 3t. There is the y2. And if I were to take the derivative of y2, I'd have 3e to the 3t, which is what I've got right here. So I wrote it as y2 prime. And if I were to take the second derivative of y2, I would have 9e to the 3t. And so I wrote that as y2 double prime. Well, notice, though, what do we know about y1 and y2? They both solve this ODE. So when I see y1 double prime plus y1 prime minus 12y1, I can replace all of this with a 0 here. Likewise, because I know y2 solves this ODE, then I can replace all of this with a 0 here. And so I'm left with 2 times 0 plus 3 times 0, which equals 0. And so I have just shown that y3 solves the ODE. So the key way to look at this, folks, is that when I have two solutions to a homogeneous linear ODE, then I can take any combination of those two solutions and I still have a solution to it. That's part of the reason why the set of all solutions to a linear homogeneous ODE forms a vector space. Okay? And the only other question I have on this is I asked, well, what would be the 0 vector in this vector space? And notice that this solution right here, y sub x, which is identically equal to 0, this solves the ODE and behaves the way the 0 vector is supposed to behave. So what you could then do is you could go through and then also verify all other properties, the closure properties, and then the eight axioms of a vector space. You could verify that all of those hold. And so for that reason, the set of all solutions to this homogeneous second order ODE forms a vector space. And hopefully this motivates why we need to be talking about vector spaces at this point in our differential equations course. So jumping to that last page there, I have just a couple more things to say. One is that anytime that collection of objects on our page 2 satisfies, anytime a collection of objects satisfies all of these requirements on page 2, then we can go ahead and call it a vector space. So for example, the set of all 2 by 2 matrices is a vector space. And I won't write it out, but that's assuming that we've got the real valued entries to the matrix, and we're using the same matrix addition and scalar multiplication that we typically use with matrices. Well, then that forms a vector space. Okay? We said that the set of all functions, real valued functions, forms a vector space, but so does the set of all continuous functions. And many of the collections of objects that you've worked with in your mathematical career form a vector space. And in our next work, we will talk about the collections of objects that maybe don't form a vector space, and we'll learn some quick checks that we can do to see whether or not something constitutes a vector space. In the time that remains, go ahead and read through my comments here. I don't have a whole lot to say, except I want to highlight this one right here. When we go to prove that a collection of objects forms a vector space, it's going to seem kind of redundant because usually you are already used to using the properties that we are supposed to be checking up on. And that's why sometimes this feels really frustrating for students, because you know that you can interchange two functions when you add them together, that if you take 2 plus the sine of x, that's the same thing as the sine of x plus 2. But if we're choosing to think of functions as a vector space, we have to at least mention that we've got the commutative property. But I can completely understand why that sometimes feels frustrating for students. And then the last thing I want you to do is just watch the last 6 minutes. You already started his chapter 16 video. Go ahead and watch the last 6 minutes of it here. I think it gives a really nice motivation for what we're doing at this point. And I will see you all next time. Take care, folks.